All right, review. Really the next, today, really through next week, is just a bunch of like, here's how Dirac Notation works. And as much as, you know, we started out with oh, here's a state. And you're probably still associating that with the wave function, like e to the ikx, which I'm telling you is good. That's a good way to start thinking about it, but it will become more wealthy in content as we progress, especially as we learn more about how to interface it with a bra. As we do more and more of this, you can see that these actually they're more than just wave functions. And of course, the bra is so complex. I'm not even going to try to describe what it is. It's like the wave function turned the other way. That's a good way to describe the symbol, but that's not what it is. I don't even know what it is. Let's see here. Okay, so we also learned. Let me just remind you about some of the complexity. This one's kind of important because it's part of the homework question coming up. When you have an operator that's sandwiched in between a bra and a cat, and as for why you would run into this, I don't think you've even seen this yet. We're going to get into this today. This is how you represent, this kind of symbology allows you to represent operators as matrices. And that's very useful. You're going to do it on a lot of homeworks too. Okay, just want to point out that I reviewed this actually a couple of times, that if you want to flip these over, it becomes its transpose. Last time we talked about Hermitian operators equal to their own transpose. That's for the most part what you're going to have. And then as we go further, there's a couple of examples of, we're going to do a couple of operators that are not equal to their own transpose. We'll talk about how to deal with that. It is weird, very weird, but it can be dealt with. Let's worry about it when we run into them. Okay, so the operator has to become its transpose, and because I flipped the bra ket, it's now a complex conjugate, whatever it is, and what is it, we'll recover it today. Actually, it should be a number. I think that's a number. I'm not even sure. Okay, so we talked about I forgot. See, I told you I'm out of it today. Okay, so we talked last time about, let's take an arbitrary state, and in a particular basis, and I think I used this notation, and be careful about dash, double dash, those are just placekeeping things, like in MATLAB. Now remember your first assignment in MATLAB where you had to do the powder XRD program? You had to have two sums, one from I equals to the number of atoms and one from J equals to the number of atoms, and you calculated the distance in between. This is like I, right? So this is from I equals 1 to the number of basis states. So that's its purpose. So that's why if I have a dash or a double dash, that's just like I versus J. That's meaningless, right? It's just a letter that you use in the sum. Okay, so we talked about this. I then mentioned how we can think of, how did I do this? I did a little bit of a proof. Let me not repeat the whole thing. Let me just cut to the chase because I'm kind of wasting a lot of time. I showed you this. Okay. And this being an inner product is a number. It could be a complex number. It likely is. You never know. You just roll with it. As we do things, you will. Yeah, what you see is. Sorry, I've already done this, right? Here, let me do it this way. Here we go. Okay. No, that's bothers me. I want it to look good. It doesn't look good below. There we go. I like that. Okay, so we can take a state and decompose it into a basis state. Now, the basis state if we're talking about, we have to figure out what our Hilbert space is. Our Hilbert space, in the case of a particle in a box, is just the x-axis. That's easy, right? If we're talking about hydrogen atom, it's x, y, z. Oh, wait a minute, that works, but it would be better to use quantity to phi. Okay, that's Hilbert space. And spin up, spin down, it's up and down, right? So they can get abstract. Let's not worry about that. We'll get into that. Okay, with Hilbert space defined, you're going to have, I don't know, some kind of operator. It's probably the Hamiltonian. And the Hamiltonian gives you an infinite number of wave functions, like all the particle in the box states when there's an infinite number, such that if I drew anything else, which doesn't have to be a particle in the box state, it can be literally anything, but it can only be on the x-axis because we have to work in the same Hilbert space, right? I can't describe my cat wave function on an x and y axis when I only have particle in the box on the x-axis. That's just stupid, right? Okay, so there's this. Inner product shows you what the, so this is the expansion of the basis set. This gives you, we already know this is an inner product. This is actually the expansion coefficient. And we also learned that, therefore, this is equal to 1. Because look what I've done. I've got gamma is equal to something times gamma. Well, that something better be the number 1. So that's called an identity. Now, you've hopefully heard that before. An identity matrix. Oh, I didn't draw the bracket right. That bothers me. When I have big zeros, it means that every other element is 0. So that's what that means by the way. You've got to get used to that. Okay, an identity matrix is not the number 1. It's ones across the diagonal. Just another thing to get to know. Okay. So, so this thing has some terms when you sum over all states in a basis state of a basis. You have to again be able to describe, as I keep talking about my cat's wave function as some kind of sum of those states. This is the number 1. It's called the identity operator. It's also, I want you to know the terms. Completeness relation. You know, we have multiple words for the same thing. But you need to know what they are in case you run into them. Completeness relation to closure. I'm not testing you on that. I don't care. I can spell all this stuff out. Okay. All right. What's it good for? Again, I hope this is kind of obvious. This is just kind of some symbology. All right, but what we're going to do with it is we're going to do stuff like this. Okay, now that hopefully is the number 1, right? We know that's an inner product. This is probably it's a wave function, and this is asking how much of this wave function is similar to the same wave function. I don't know, that probably ought to be exactly the same. Or that'd be weird. It's also a statement of normalization, right? It's both things at once. Okay, so I get that. So now what I'm going to do is I'm going to insert a completeness relation. I'm going to add a closure. I'm going to resolve the identity. Those are all the same thing. I got you. You got to know this stuff because you're going to hear all 3. Something that drives me absolutely donkey nuts. Apparently I'm donkey nuts today. I just hate how we have so many words for the same thing. It's just like, why do we do that? Anyway, but we do. I can't change. Fortunately, I know them all. Okay. All right, so I've slipped the number 1 inside of this inner product. All right, now what I recognize is that this is the complex conjugate of that. Right, so now you see, now I'm actually using some of the symbology in a way that's a bit more meaningful. Now, you know that based on what I wrote before, that this thing is the coefficient. So what I've got here is the sum of the expansion coefficients That's the complex conjugate times itself, the number, not the complex conjugate. Okay, now give me a symbol for that. Complex conjugate times itself is what? Huh? Absolute value. Here's the correct symbology. Sorry, my A's are. It's always bothering me to write A's. I don't write stars correctly. Oh, the absolute value is slanted. No slant. No slants. No, it's slanted the wrong way. There, now I got it. Oh, it's got a deal. I have to look at that. 1 point. I don't want you to think that that's another absolute value. 1 point. Okay, so the sum of the expansion coefficient, so I write my cat wave function as the sum of states. Those coefficients better add up to, sorry, the sum of the square of coefficients better add up to 1. Now, you might recall, I don't want you to forget this stuff, when we were talking about our X-polarized silver atoms in the Stern-Gerlach. Remember this? So it's half SZ up and half SZ down. Why did I write 1 over the square root of 2? Right, I'm writing the square root of the weight. If it's half, then in the expansion, it's actually the square root of that number. So I even show undergrads this stuff. Mostly because I can talk about my cat with my examples, right? Okay, so again, more Bra-Ket notation. Just let's do stuff with Bra-Ket notation. There you go. Lots and lots and lots and lots of examples. Okay, now let me remind you of that I gave an example of a Stern-Gerlach machine turning SX plus to SZ plus. I gave you a little example of that. And I showed you a matrix that allows that to happen. In the SZ basis, XX plus, I keep forgetting that 1 over square root of 2. So remember I told you that the Stern-Gerlach apparatus is like an operator. This is the operator. Again, last time, you saw this before, I just keep forgetting that square root of 2. And this in the SZ basis is SX plus. Now notice I was very careful about what I said. I wanted to make sure my XZ plus minus blah, 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 I'm not getting that wrong. So I have to really focus on this. Okay. This is basically, this transformation in a machine can be equated to an operator. That turns SX plus to SZ plus. In a basis set of SZ, this is SX plus. Now this is, sorry, that's the identity operator. This is the operator that allows that to happen. What you end up with is the component, this is our weighing coefficient. There it is. 1, 1, 0, 1, 0, 1, 0, 1. And sure enough, this is SC, that's SC plus. There you go. How do I come up with that? Now, partially I can just kind of figure it out. You can kind of play with these things. If we turn SX plus to SC plus, you can write this over there, and it really wouldn't be too hard to figure out what matrix does that. Or we could Dirac notation tells us how to do this. Okay, here's how this is going to go. This really isn't hard, but it's a lot. It's a lot of stuff. It's like a very complicated Sudoku puzzle. Okay, so I'm going to add 2 closures. I'm going to resolve the identity twice. Okay, there's one identity. I want to make sure you can see it. These parentheses don't mean anything. want to make sure your eye is drawn to the closure. And you can see it correctly. So remember, I just multiplied this operator by 1 on the left, I multiplied it by 1 on the right. Okay. So there you go. Let me write this in a way that's a little bit more like what you're going to see in the book or in the talk. I'll write the first sum up front. I'll write the second sum right behind it. There's nothing wrong with this. There's no algebra involved in what I've done here. This is just a restatement. And what I've got is this. And now you are seeing, sorry. Now you're seeing an example of what I had put up before here. I know this was just teaching you how to manipulate the symbology, but now you're seeing now you're actually seeing an example of a bra operator ket. Now remember, what I'm doing here is I'm trying to figure out how to represent an operator with a matrix, and I've actually done so. This is like, that's like the column, the row, that's like the row, and that's like the column. Right, so you kind of see that, right? So sums, like here, when it comes to the Hilbert space above down, there's only 2 members of the sum, up and down. And so this is this, and this is that. Put those together, of course, it's a square matrix. So again, you're seeing now how to represent operators as matrices. Okay, now this is really big, and this is what we're going to be doing. Draw a star. This is what we're going to be doing over the next month. Now, of course, operators tell you things in quantum. They tell you how to solve wave functions, so that's pretty important. All right, now let's go further. By itself, this is, hopefully now you're seeing a little bit more about how we can kind of transition between Dirac notation, between, of operators. You know what the operators already are, like the Hamiltonian. Anyway, they're all connected. This is how. All right, now, let's say if the states are eigenstates, that would mean both ket and bra, or eigenkets and eigenbras of gamma. Now, on an exam, I will tell you, you better, I'm not going to give you this on a cheat sheet. You should know this. What's the spin of the SZ plus state? Why, that's 1/2 h bar. SZ plus. It's just the eigenvalue equation. Okay, now let's do that here. And I could have it work on its eigenbra, but instead I'll have it work on its eigenket, because that's always way easier. I get really confused when I'm dealing with bras. That just confuse me to death. So I just don't. I look at the ket. I'm gonna look at it on the right. Okay, what does that turn into? Okay, if that's the case, and again, I hate not having a bigger board. Okay, so when it acted here, it released the eigenvalue, and that's a number. I can put it anywhere, so I'm going to put it there. Tell you what. Let me make this a little easier. I'm kind of screwing up here. Let's look at this element, and then I'll put it in the sum. Sorry, I'm trying to do 2 steps at once. That was stupid. Okay, again, let's have it act here. Okay, that's A prime. Again, that can come out. Look at that. Okay, inner product of a state of the operator not with itself or not itself? The answer to that is that it's a Kronecker delta. It'll be 1 if, so remember, I haven't really said what the double dash and dash are. It's like from I equals 1 to the number of atoms, for j equals 1 to the number of atoms. They'll cross each other. Sometimes we're all the same atom, right? And that's what the delta function does. If we're not on the same basis, then that's 0. Again, my point being is that I know that I have a double dash here and a single dash here, but the double dash can be the single dash. The single dash could be the double dash. It could be triple dash, it can be anything. I haven't really said what they are. Maybe that they could still be each other. Anyway, if that threw you off, the more we do this, it'll make more sense. So now here's where I was battling before, and I should have shown this first, I just wasn't thinking. Okay, now, now I've got my A double dash, but the thing is the Kronecker delta says you can wipe everything out. Everything is 0 unless A double dash is A dash. It also kills one of the sums, right? So you can look at this and say, so you can actually do a couple of things with this. Let me give the easiest one. You can look at this and say, well, okay, when I'm doing this sum, all the terms in the sum, and I don't even need to look at this because that confuses me. I just won't even look at it. I'm looking at this, and I know that I have a Kronecker delta. I know that no matter what the heck is in there, it doesn't even matter what it is. Unless A double dash is A dash, unless they're the same, then everything's 0, leaving only the A double dash equals A dash, only that survives. That means that the sum is now gone, it's been dealt with. The sum has already been summed. Everything was 0, except for one term, where A double dash was A dash, leaving behind this one. The second, leaving behind this one right here. And now I can rewrite the whole thing. Okay, so again, A double dash, this used to be A double dash, but now it's A single dash because of the delta function. Same thing's here. There we go. Okay, this is 1. Okay. A dash. Okay. So there you go. Now, that's fine and good. So now I've got an operator that is now in the form of a ket bra. Remember, a bra ket is an inner product. It's just a number. This is a ket bra. Bra ket number, ket bra operator. Now, to look at that, now you got to interpret that. Now, I'm telling you what you want to do with this is make this a matrix. Because whatever problem is being asked is going to be best solved. If I'm using this language, you want to be using a matrix. Now, how would I put this in matrix form? This is actually really easy. Now, again, you can think of the way to think of this. When you draw one of these matrices, you've got to know what the rows and columns are. And then, of course, you have cross terms that fill it out because it's squared, right? Now, if you're in the A basis, these are your columns, and we'll stop there. And these are your rows. And we'll stop there. Okay. Now, when I look at this, you see, let's go back to this. Remember, this is actually the most general representation. Let's look at this, and then let's see if what I do with this is consistent with this. This is for things, the states being eigenstates. This doesn't claim that. So let's look back at this. This is the innards of the matrix. All right? Now let's see what happens when A dash is equal to A double dash is equal equal to A dash. Well, that's what we did up here. The result is the eigenvalue. That's not a ket or a bra. You don't draw kets or bras inside of the matrix. You put numbers, real numbers. Okay. Now that also means that now if I look at all the other elements, A dash, A double dash, well, A double dash truly is not the same thing, or A double dash is actually A triple dash. If these are eigenstates, then I've got my Kronecker delta, and that means that everything else is 0. Okay, now let's go to the next one. A double dash, A double dash. Okay, that's going to simply, and again, but now I'm looking over here to, I'm saying that these are eigenstates. That's now the second element. That's now the second element of this sum. 0. Dot, dot, dot. This is how you do this in the matrix notation. You write this dot 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 dot. That means that it goes on and on. I'm doing that case the basis. Perhaps the basis is infinite. Anyway, you'll see that in your book. Okay. So I can tell you that again. This is the most important, about the most important Dirac thing that we have. This is very important. When you have an operator and you're working in the basis state of that operator, which is a fancy way of saying this, then everything is easy. This is what's called easy. When everything is diagonal, everything is easy. We will deal with times when the basis and the operator are not okay with each other. Right? An example, momentum and sine functions. Right? Those are not cool with each other. What do? Well, you make this, and then you can figure it out. Actually, you know what you can do with this? Let's say, if it's a matrix, what did you do when you had your last homework? We had a matrix. What did you do? You had a Hamiltonian matrix. What did you do with the matrix? You found the what? You get the eigenvalues out of it. You can also get the eigenvectors. So I can tell you that if you're interested in the eigenfunctions of this operator and the eigenvalues of this operator, you make this matrix and do it in MATLAB, which you're going to be doing. And you say, hey, MATLAB, what's the eigenvectors? What are the eigenvalues? And it just spits it out. Now, one thing about a diagonal matrix. Okay, so I make this matrix. 1, 0, 0, 0, 2, 0, 0, 0, 3, blah, blah, blah. Hey, man, what are the eigenvalues? 1, 2, 3, on and on. It'll spit out the diagonal terms. That's just matrix. That's just what matrices do. Hey, MATLAB, what are the vectors? What are the eigenvectors? 1, 0, 0, that means this. 0, 1, 0, that means this. 0, 0, 1, that's that. See what I mean? 1, 0, 0, 0, 1, 0, 0, 0, 1. See, that's how it works. Now that's for a diagonal. So if you're doing that with a diagonal matrix, you're wasting your time because you already know. Right? You couldn't have written the thing without knowing that already, so you're kind of dumb. All right, what happens when you have a matrix and you're not working with its eigenstates, like momentum, and you have sine waves, sine and cosine? Well, this fixes it. Right? You'll have off-diagonal terms. That's what will happen. But you go into MATLAB, you say, hey, what are the eigenvalues and eigenstates? And it tells you. Now you know the eigenvalues and eigenstates of that Hamiltonian. And that Hamiltonian's that operator. Maybe the operator's a Hamiltonian, and that's the most important thing you could ever know. Anyway, I know this is all a lot. So as I try to fix up your homework, I have a prototype written. I'll have you do stuff with this. It's way easier. I have to put it this way. I don't have a choice. But when you start putting numbers into this, it'll be a lot easier. Okay, last bit. And this part, I hope you think is cool. All right, let me go ahead and give you an example. There's one more thing you need to learn about operators. But we're not going to really be doing Dirac notation. We'll take a little break at Dirac notation. Let me ask you this. Okay. Huh? Ta-da! What? One? Oh, I'm sorry. I'm sorry. I didn't write that correctly. Now what is it? It's kind of cool, huh? What do you think? By the way, the answer is 2, but I think it's 2. We'll work on it. What do you think? Is it either 1? Now again, this is not this. No. I didn't write that. E to the operator. Operating on X. EDX you had no problem with. What's the derivative of X with respect to X? Some of these spit out 1. Well, that's pretty good. Now E to that operator. Operating on X. What do you do? Maybe this is mathematical nonsense, right? Like an eigenvalue equation that doesn't spit out its eigenvector again. Just jump.
You have to take the natural log to get the
I don't think that would. All right, so the problem there is that you'd end up with a natural log. Actually, I'm not too sure. You know the problem is that you have to take. You're trying to take the natural log of this by itself.
Yeah.
You can't do that because you changed it. You have to take the natural log of the whole thing, and then you actually still have the same problem.
All right.
Because then you can deal with this, but then you're left with the natural log of that. So no matter what you do, you're going to have a problem.
All right.
All right, what else could you do? All right, now do you remember how I did this? How did I come up with that? How do you prove that? This is a little textbook. I think I did it in class. Euler's equation or something. How did I do it? I didn't just write it down, I proved it. Huh?
I'm not sure. Expanding into the bar I
Expanded it. In what kind of, so give me a math term for an expansion.
binomial.
Is it Taylor series?
Taylor
A
series.
Taylor series. You can do a Taylor series. What's next? Yeah, see, now this isn't quite right. It's like half of 6. Anyway, all right, you get the point. You can have e to a derivative. The fact that you can even, that is not just crazy junk, a child writing stuff down. The fact that you can do that, it means it's a thing. It's actually an important thing. Here's what we're doing. We are doing functions of operators. I'll give you some silly examples at first. So here we've kind of covered what to do, but now here we know what to do with that. But this, what do you do with that? How do you do with functions of operators? And I'll give you we're going to do 1 or 2 examples that you already know the answer that are stupid. But then we're going to do e to the derivative. We'll do it again. Okay, the way to deal with this, and I know that this is, I'm writing a Taylor series, but then there's also, I think it's called a Maclaurin series. What is it again? And I forgot how it's a form of a Taylor series, if I'm not mistaken. Okay, so I think this is a Taylor series. The Maclaurin is when C is 0. It's something like that. Anyway, I want to make sure that you see this in the most general form, right? So this is f of x expanded about whatever C is, in case you want to center you're doing this because you're approximating the function. And you want to make sure that, you want to be as accurate close to the number C for whatever reason you have to do that. I don't know why you're doing that, but that is what you're doing. So at point C, everything is correct. The derivative, factorial. So you can see at point C, you're getting the exact right answer. Anyway, now there's, I think this is how your book does it. And so I want to make sure that you understand one thing that can be very confusing. Okay, what's very important, and now of course you see what I'm trying to do here. X is, let's put the operator in for X. Okay, so that's what we're doing. Okay, but this is important, and I think this is how the book does it, but they don't explain this. C is 0. The reason is that the concept of expansion about a number on the x-axis, that is completely non-applicable. It doesn't make sense. I'm talking about an operator. What number on the x-axis am I expanding about? None, because the concept is stupid. It just doesn't apply. So, therefore, you're going to plug in 0. You're going to plug in a 0 for this thing. Okay. So where am I at? Okay. I'm sorry. Got myself a little lost here. Well, anyway, yeah, just plug in a 0. Plug in a 0. Now, let me give you some examples here. Okay. If we'll work with eigenstates. So I'm just writing down, I'm actually writing the eigenvalue. If this is the case, okay, now this is the take-home message, and then we're just going to work some examples. Now, remember that an operator, if I don't do something, right, like, oh, why am I operating on a ket? Because that's the purpose of the operator. I might as well put it in this context because it's kind of stupid if I don't. What you're going to find is that it's equal to the function of the eigenvalue. Okay, so this is the take-home message right here. Oh, yeah, that came across. So this is important. Let's do 1 or 2 examples. We've got 5 minutes left, and I can do 2 examples, and that's all the examples I have. Okay, so let me tell you real quick what's going to happen is you're going to have these weighing coefficients. These are just numbers. And this is the operator. So you're going to have no operator, the square of the operator, the cube of the operator. Out here will be your ket, and then you have to bring the ket through the entire sum and see what happens. You'll end up with a summation with 1 plus the eigenvalue plus the eigenvalue squared plus the eigenvalue cubed. The Taylor series of which is f of that number. That's the big picture. This is how this is going to work. So let's do 2 examples and that'll be more clear. So this formula I just gave means this. So this means that. I know that's not really clear right now, so we're going to do 2 examples and then it'll be more clear and you'll actually do a few on your homework. Actually, really a bunch of these. This comes up a lot. Okay, so let's do the simplest example possible. Momentum. I'm not going to worry about h bar over I derivative. Let's not worry about h bar over I. That's just going to confuse me. I mean, you get the essential parts now. Okay. Now, the question is, what is this? What is that? Okay. Well, this is the operator. In our language, f of the operator is the operator square. Now, let's be more plain spoken. Let's try to make it a little familiar. It's just the square. F is x squared. Right? I just want to make this more familiar to you. This is really what we're doing. Okay. Okay, so what do we do? The state, you know what? I'm going to go ahead and preview a little bit. You don't know this yet. But I'm going to go ahead and preview. Okay, I didn't say that the ket was e to the ikx because it's not. But an x bra onto that. Now, we haven't covered this yet, but I just want to go ahead and preview how we get wave functions out of Dirac notation. This is actually what a wave function is. Okay, so, and therefore, now this is clearly an eigenstate of the derivative of the momentum operator. Let's do that. Tell you what. Let me throw that in there because I hate this screen on. That's going to really complicate things. Okay, if you don't mind if I do that. So h bar. Sorry about that. I want to make this as easy as possible. Okay, so the function of the operator. Acting on now I'm just writing this out, and again C is 0. So I'm just going to write down the formal definition of all of this jazz. And I'm only go to a few terms. I'll write this out that way. Need to bracket it because now I've got to use ikx. Okay, now the thing that is a little difficult is what is that? Okay, now this is why I wanted you to be on familiar ground with f is x squared. So what is the function at 0? Huh? 0. That's 0. Okay. The derivative of x squared is what? 2x at 0 is? Double derivative? 2 over 2. And then, so again, we got the derivative twice. And of course, the higher orders will, the higher order derivatives are 0. That's it. Yeah. Folks, is this right? Is the momentum operator? Momentum operator, and again, I've used h bar. I've used h bar as 1. Is this not correct? If h bar is 1, it's minus the derivative, double derivative, right? What's minus the double derivative? What's minus the double derivative of UPIKX? -1 times -1. There you go. See, it works. I'm using h bar as 1. And you can do that for a bunch of reasons. I'll show you on a homework. I'll do it on the homework.